In this video, we're going to look at series. You've learned about sequences. A sequence is just a list, an infinite list of numbers. You can look at it that way. And a series, what we're going to do is we're going to, roughly speaking, add up all of those numbers. And we ask the question, well, when we add them up, do we get a finite value? There are lots of subtleties there, so that's a little bit rough. Along the way, we'll learn about geometric series, we'll learn about telescoping series, and we'll learn the divergence test, which is a way to look at the terms of the series and say, no, there's no way this could converge, whatever convergence means. I like to open up this discussion with a little puzzle here. I have a square. The length of each side of the square is 1 unit. And our question is, what is the total area of the blue region? Okay, so I open this with my students and ask them how they might go about it. And often this is the response that I get. They say, well, what we could do is we could figure out the area of each of the squares. So let's take this first square. I'm shading it a little bit darker here. The area of that first square, since the entire square is 1 by 1 or 1 unit, the area of that first largest square is going to be 1/4 of a unit. How about the next square? Well, the next square, the next largest square is here. And, well, it is 1/4 of 1/4, is it not? It's 1/4 of that. So it would be 1/64, but I'll just say it's 1/4 of 1/4. And you can probably see the pattern that's developing here. Now this square here, I don't have a lot of room there, that square is 1/4 of 1/4 of 1/4. So that's 1/4 of 1/4 of 1/4. And that pattern will continue. So we end up with 1/4 plus 1/4 squared plus 1/4 cubed, and so on. Okay, so that's lovely, but it doesn't answer our question. We have a representation for what the area is, but we don't know what the area is. So then I suggest to the students, well, let's just pretend we stop after a certain point. What if we just stopped after that first calculation, after that first term, after 1/4? Well, then clearly the answer is just 1/4. If we stop after the second one, we would have 1/4 plus 1/16, which is 5/16. Okay, so let me highlight these. We've got 1/4. The next one is 5/16. And then I would have 1/4 plus 1/16 plus 1/64. Which turns out to be 21/64. Okay, now here's the easy way to do this. I got 21/64 by adding 5/16 to the new number in my term, or in my sum, the 1/64. So let's go one more step here. Let's get rid of this. One more step, we'll have 1/4 plus 1/16 plus 1/64 plus 1/256, which is, we're going to get a 256 in the denominator, and in the numerator we end up with 85. So I have here, essentially what I've done is I've created from the sum a list of numbers. Well, I've created a sequence. Now let's look at the decimal approximations for each of these. We get 0.25 for 1/4, 0.3125 for 5/16, for 21/64, 0.328125, and 0.33203125 for that one. You notice those numbers are getting close together, and they seem to start a little trend of 0.33 maybe something, which reminds me of a third. And in fact, if you subtract 1 from each denominator, 1/3, 5/15. Oh, that reduces to 1/3. 21/63. That reduces to 1/3. 85/255 reduces to 1/3. So it seems like these numbers are really darn close to 1/3. So I'm going to guess that the sum is a nice 1/3. Now, let's see if we can see from the picture how that is. Once we know it, it's kind of fun because the students light up and they say, hey, I can see why it is. If you don't, pause the video and see if you can determine why this sum is 1/3. Okay, so here's why I know it. I'm going to take each of the regions here of the same size. I'm going to take each region of the same size and kind of block them in. So here is one that's large. There's another that's kind of large. And here's a third that's kind of, a third, I get it. There's a third that's kind of large. What fraction of those are blue? 1 out of 3 of them are blue. 1/3 of them are blue. The next largest size, I have 1 that's blue, 2 that are orange, 1 out of 3. 1 out of 3 for the next largest size, and so on. So you can see the 1/3 popping out of the picture at that point. So the question is, how do we determine what we mean by these sums approaching a number? First of all, let's develop some notation. We're given a sequence a sub n. Our sequence was essentially the powers of 1/4, which is a geometric sequence, if you remember that term. An infinite series is the sum of all those terms in the sequence. So we're going to use this notation. Now here's something that we practiced just a minute ago. Given a sequence, the sequence of partial sums is defined by taking the sum of the first certain number of terms. So a sub 1 is just going to be s1. a1 plus a2 is s sub 2. We're going to call that new sequence s sub n, which is the sum of the first n terms. So s sub 5 would be the sum of the first 5 terms. Okay, up here, our sums, the first one was A1 or S1. This is S2, S3, and S4 because we added 4 terms to get there. What do we mean for a series to converge? A series converges if and only if the sequence of partial sums converge. Wow. Okay, so a series is built up of terms of a sequence. From those terms of a sequence, we create a new sequence called the sequence of partial sums. If that sequence converges, then the series converges. Okay, so in the sequence video, if you watched that, we investigated this sum. 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over n squared, which is we wrote in this notation. This is the sequence of partial sums for the sequence of reciprocals of squares. We talked about the fact that this sum, or this sequence of partial sums, approaches pi squared over 6, and so we're going to write the sum n equals 1 to infinity of 1 over n squared to be pi squared over 6. Again, what that means is that if we stop this sum at a certain number, let's say 4 billion, that number of reciprocals, when we take the sum from 1 over 1 squared to 1 over 4 billion squared, we're going to be pretty darn close to pi squared over 6. Take, for example, this sum. The sum n equals 1 to infinity of 1 over n cubed plus 6. In this particular sum, the terms are 1 over n cubed plus 6. The sequence of partial sums, well, s sub n would be 1 over 1 cubed plus, 1 cubed plus 6, plus 1 over 2 cubed plus 6, plus 1 over 3 cubed plus 6, plus boop, plus 1 over n cubed plus 6, because we're looking at the nth partial sum, there. So the terms are the 1 over n cubed plus 6. The partial sums are these guys. Now, it turns out that one of these can converge while the other doesn't. Okay, I'm not going to tell you which. Yes, I am. This might converge to a number, but the sequence of partial sums may not. So we've got to be watchful for that. Okay, so one thing I want you to notice in this definition or in this result, a series converges if and only if the sequence of partial sums converges. That if and only if is a two-way street. Okay, so if a series converges, then the sequence of partial sums converge. On the other hand, if the sequence of partial sums converge, the series converges. If I tell you I'll go to Chipotle for dinner if and only if I have $10, then you can determine how much money I had whether or not by looking at whether or not I went to Chipotle. If I went, I had $10. If I didn't, then I didn't have $10. Also, if I have $10, then you know I went to Chipotle. And if I don't have $10, you know I don't go. Our first sort of nice character in our play here is the geometric series. A series is a geometric series if we start off with some term A. Each new term is some constant multiplied by the previous term. So here I go from A to A times R. We multiplied the first term by R. If I go from AR and multiply that term by R, I end up with AR squared. If I multiply that by R, I end up with AR cubed. That would be the next term. It turns out that this is convergent if and only if the absolute value of R is less than 1. Moreover, this is a very rare circumstance. This is exciting. If it converges, we know the value it converges to. So our sum will converge to the first term divided by 1 minus that common ratio, A divided by 1 minus R. And I've already given you the tip here. A and R can be thought of as follows. A is the first term of the series, R is the common ratio. Common ratio we get by looking at how much we multiply each term by to get the next. Or you can divide one term by the previous term to figure out that common ratio. Now be careful, not every series is going to be geometric. In fact, not very many of them that you deal with will be, but when they are, we know what their sum is. Again, knowing the sum value is a rare circumstance. We want to verify that the answer to example 1 is as we suspected it. So if you remember, that was, and I'm going to write it in slightly different fashion, 1/4 plus 1/4 squared plus 1/4 cubed plus 1/4 to the 4th, and so on. Okay. We found out that this was 1/3. Let's see if the formula works for us. So our common ratio is how much we multiply each term by to get the previous term. Well, we learned that we just multiplied by 1/4, right? If I multiply 1/4 by 1/4, I get 1/4 squared. Multiply that by 1/4, I get 1/4 cubed, 1/4 to the 4th, and so on. So our common ratio is 1/4. Now here's the unfortunate thing, maybe. A is the first term of the series. In our case, A is going to equal, well, the same thing, 1/4. According to the formula I was given, the answer should be A over 1 minus R. Now, I should check something. Is the absolute value of R less than 1 in absolute value? Or is the absolute value of R less than 1? So is the absolute value of 1/4 less than 1? Why, of course. Okay. In our case, let's go back to the formula. I get A over 1 minus R. A was 1/4. 1 minus R is 1 minus 1/4, which is 1/4 divided by 3/4, which is 1/3 as we suspected. So the formula does work in that particular case. It works in all cases, but we are now a little bit more convinced of our answer. Okay, what that means is, and here's the big thing, I'm going to reiterate this in a moment. The terms of the series, in our case, we learned this in the sequence section, go to 0. If you have a geometric sequence where the common ratio is less than 1, as you look at larger and larger powers, they go to 0. In fact, they go to 0 so fast that by adding them up, we don't go off to infinity. Okay? So the terms of the sequence, or the terms of the series, go to 0 fast enough that the series converges. Okay, so let's look at some other examples here. I have 4 minus 2/3 plus 1/9 minus 5/5 or 1/54 plus 1 over 3/24. I want to know if this series converges or if it diverges. And if it does converge, we want to find its value. If it diverges, it doesn't have a value. That's kind of nonsense. Okay, so let's look at this first example. 4 minus 2/3. So what I'm going to do is I'm going to take the second term and divide it by the first term. We're going to get negative 2/3 divided by 4. Well, this turns out to be negative 1/6. It's like negative 2/3 times a fourth, which would be negative 2/12, which is negative 1/6. Okay, so if the series is geometric, the common ratio is negative 1/6. Let's try a couple more, or maybe one more, and then I'll tell you the way I tend to do this. I'm going to take 1/9, take any term divided by the previous term, divided by negative 2/3. Well, that's 1/9 times negative 3/2, which reduces to negative 1/6. Okay, so I have two in a row. Let's go for broke here. Here's what I tend to do instead of doing that division. Once I have my first ratio, I just multiply that by each term to make sure it gives me the next term. Currently, I am at 1/9. If I multiply that by negative 1/6, yes, we end up with negative 1/54. If I multiply that by negative 1/6, the two negatives multiplied together will give me the positive. And 1/6 times 1/54 is indeed that. So that seems to be the right thing. This will be our R value. Is the absolute value of R less than 1? Check. Okay. So our sum is going to be the first term. A is 4. So we end up with 4 divided by 1 minus negative 1/6, which is 4 divided by negative 1/6. 1 minus, that's going to be 7/6 in the denominator. And when we take the reciprocal of the denominator and multiply, we end up with 24/7. Okay. Let's try the same thing in the next example. Okay, so I'm going to take 6 and divide it by 5. Well, that's like 1.2. And then I'm going to take 7. No, I don't want to do that. Let's do this easier. Let's take 6 and multiply it by 1.2. When I do that, 6 times 1.2 is indeed 7.2. And then if I take 7.2, multiply it by 1.2, what I believe the common ratio to be, I get 8.64. And if you multiply that by 1.2, you end up with 10.368. Okay? So it is the terms do form a geometric sequence. If I look at the R value, it's 1.2. Is the absolute value of R less than 1? Well, of course not. Absolute value of 1.2 is not less than 1. So this series diverges. Okay? The terms of the series do form a geometric sequence, but since that common ratio is greater than 1, it diverges. And for our last example, I'm not so keen on this one. I'm going to write out several terms of the sequence who are in our sum, and then go from there. So when n is equal to 1, I'll have 2 to the 3 times 1, so 2 cubed divided by 3 to the 2 times 1, 3 squared. When n is equal to 2, the numerator, it's going to be 3 times 2 in the exponent, 2 to the 6th. The denominator is going to be 2 times 2, which is 4, 3 to the 4th. If n is equal to 3, we end up with 2 to the 9th divided by 3 to the 6th. 2 times 3. And if n is equal to 4, we'll do one more of these. We end up with 2 to the 12th divided by 3 to the 8th. Is there a common value that we keep multiplying by each time? Well, what do I multiply 2 to the 3rd by to get 2 to the 6th? I multiply by 2 cubed. What do I multiply 3 squared by to get 3 to the 4th? I multiply by 2 cubed. Each time we're multiplying by 2 cubed over 3 squared. If you multiply 2 to the 9th over 3 to the 6th by 2 cubed over 3 squared, we end up with 2 to the 12th over 3 to the 8th. That will be our common ratio. Is this less than 1? I don't know. That would be 8/9, and that's less than 1 even when I throw the absolute values on it. So it will converge. We need to know the first term. Our first term is a, which is 2 cubed over 3 squared. Hey, that looks familiar. It's 8/9. And so a over 1 minus r is 8/9 divided by 1 minus 8/9, which is 8/9 divided by 1/9, which turns out to be 8. This sum will be equal to 8. Interesting. We're going to look at a few applications of the geometric sequence, or the geometric series here. The first is a joke. Infinitely many mathematicians walk into a bar. The first one says, hey, give me a beer. The second one says, give me half a beer. The third one says, give me a fourth of a beer. The fourth one says, give me an eighth of a beer. The bartender says, hey guys, cut it out. And he pours for them 2 beers. He says, you guys need to know your limits. Ha ha. Okay, so why is this a joke? I'm not even sure if it is a joke. Well, it's a joke because this is a geometric sequence, or geometric series. The first term is 1. The common ratio is 1/2, which is equal to 2. For our next application of the geometric series, I'm going to do this problem in 2 different ways, and we'll see how the geometric series comes into play. The first way, the second way is kind of a secondary way that's, I believe, a little bit easier. We're going to look at the sum, or look at 0.57 repeating. If you're not familiar with it, that little bar over the top means we're repeating this decimal. So the way I should think of this is 0.57, 57, 57, 57, and so on. Okay, now, when someone gives me this number, like 0.162, saying 0.162 to the first person who taught you decimals will probably make them cringe. They would rather you say that's 162 thousandths. Well, because our number goes on forever, we can't really do that. So what we're going to do is we're going to split it up so that we can kind of do it bit by bit. I'm going to take each repeating part and write it out. So 0.57, 0.0057, 0.000057, maybe one more, 0.00000057, and so on. Now over on the right, I'm going to write that as my decimal teacher would tell me to. The first one is 57 hundredths. The second one is 57, what would that be? That would be 10 thousandths. The next one would be 57, well, it's going to be 1 millionth, I believe. And then 100 millionth, 57 over 100 million. Okay, so what we have formed here is a geometric sequence. Notice that to get from one to the next, we're just multiplying by 1/100th. We're multiplying by 1/100th. Multiplying by 1/100th each time. Okay, so I'm going to use that formula. In our case, r is 1/100th, which of course is less than 1 in absolute value. So it will converge. Our first term is the 57/100ths. And so the sum should be a over 1 minus r is going to be 57/100ths divided by 1 minus 1/100th. I'm going to do a little bit differently here. I'm going to multiply by 100 over 100. And we'll end up with 57 in the numerator. Multiply 100 by 1, you get 100. Multiply 1/100th by 1, and you get 1. So we end up with 57/99ths. That reduces, that would be what? If I divide each of these by 3, we'll end up with 19/33. If you type 19/33 into your calculator, you will get the 0.57 repeating. Okay? So that's method 1. I like it because you can see the geometric series in action, and it's a good reason to say, hey, we need the geometric series. There are lots of beautiful applications of it. So let's look at it a slightly different way. Here's what I'm going to do. I'm going to use some variables. I don't know what the value of 0.57 repeating is. Well, I do, but let's pretend I don't. So I'm going to just give it an arbitrary variable name, x, 0.57, 57, 57, and so on. Now, multiples of x will have the same repeating part if we choose the right multiple. If I choose x equals, or if I multiply that by 10, it's not going to do it, but the multiplying by powers of 10 shifts the decimal place a certain number of spots. I'm going to multiply this by 100. 100x is going to be, oh, well, we just shift the decimal place 2 places. And so we end up with 57.5757, and so on. X, remember, was 0.5757, and so on. Now, what's nice about this is that in each of the decimal places, the same number appears. In the 10th place, we have 5s in both numbers. In the 100th place, we have 7s in both numbers. So what we can do is we can subtract each side independently. 100x minus x will give us 99x. 57.5757, so forth, minus 0.5757, so forth, is just going to be the stuff before the decimal, 57. And lo and behold, if we divide by x, or divide by 99, we get 57/99. Again, same thing. Okay? So let's do one more example that's slightly more complex here. 8.4387 repeating. So the 387s repeat. In this circumstance, we're going to do something slightly differently. I'm going to let x be this number that's unknown. 8.4387. Okay, now I'm going to line things up. Now, the first thing I'm going to do is I'm going to multiply by a power of 10 that will put the decimal point right before the first repeating part. Okay, my goal is to get it to here because the repeating part is 387. So if I multiply that by 10, I'm going to do this on a second line, so save space up top. We're going to end up with 84.387. Okay, now I need to move it 3 more spots. Okay, so I'll need 3 more zeros, so I'll end up with 10,000x. If I multiply by 10,000x, that's a total of 4 zeros. That moves the decimal point 4 spaces over. That's where I wanted to be. That's going to be, well, the decimal part will be the same, 387, 387, 387. That was by design. There will be a 387 leading into that, and then an 84. And when we subtract, we end up with 9,990 x equals 84,303. So x will equal 84,303 over 9990. This reduces to 9,367 divided by 1110. One nice little thing, and this is for simplifying, that you might be able to use it, you might not know this, but a number is divisible by 3 if the sum of the digits is divisible by 3. So in the numerator here, if you add those digits, you get 8 plus 4 plus 3 plus 3, which is 18, which is divisible by 3. So the numerator is divisible by 3. Now, 18 has another special property. It's divisible by 9. The same rule works for divisibility by 9. Since the numerator is divisible by 9, so is the denominator. Since the sum of the digits is divisible by 9, that number will be divisible by 9. And it's pretty easy to see that the denominator is divisible by 9. That's very helpful when we reduce. Okay, so for our last example with geometric series, before we do the next thing, for which values of x will this series converge? It's x to the 2n over 5 to the n. Well, I don't really know much about this, so let's play with this. I'm just going to write out some terms. When n is 1, let's see, the exponent of x would be 2. X to the 2 times 1. So x squared divided by 5 to the first, 5 plus. Okay? And then I'll have x when n is equal to 2. I'll have x to the 2 times 2. So x to the 4th over 5 to the n, 5 squared. I'm just going to leave that as 5 squared. When n equals 3, we have x to the 2 times 3. So x to the 6th divided by 5 to the n, 5 cubed. Oh, I see the pattern. Next one should be x to the 8th divided by 5 to the 4th. And then x to the 10th divided by 5 to the 5th. And so on. Okay. Now, the only thing we know right now is geometric series. Okay, we only know geometric series. So, let me erase that guy, make it prettier. There we go. I'm guessing this has something to do with the geometric series. In the numerator, you can see that each time we multiply by x squared, in the denominator, we simply multiply by 5. This means our common ratio is x squared over 5. Now, here comes the fun part. I know that a series will converge, a geometric series will converge only when, exactly when, that common ratio is less than 1. So we're going to do that. So we're going to take the absolute value of x squared over 5 and set it less than 1. Now keep in mind what that means. Absolute values measure the distance from 0. So this is saying that this number, don't even worry about what's inside the absolute values. This number is no more than 1 unit from 0. Well, if we think about a number line, and I start at 0, and I'm allowed to stray 1 unit, well, I could end up at 1, or I could end up at -1. So our result would say that -1 is less than x squared over 5, which is less than 1. Whatever number is in the absolute value has to be trapped between those two values. Now we all know that x squared is non-negative, it can't be negative. So I really want to think about just sort of this whole x squared over 5 business. In a sense, that's got to be less than 1. Okay? Now, I can take the square root. When you take square roots with inequalities, you really need to be careful because then we can actually pop back in negative values. If I take a -1, for example, -1 squared is +1. 1/5 is less than 1. So I'm essentially going to take the square root of both sides, but I'm going to have to introduce a negative. So we'll end up with x squared, or x over radical 5, and that will be trapped between -1 and +1. And when we multiply both sides by the radical 5, we find out that negative radical 5 will be less than x, which is less than radical 5. So if our number is in that range, which is kind of a nice wide range, it goes up to past 2, the series will converge. If it's not in that range, the series will diverge. Later, when we learn the ratio test and we learn about power series, we're going to talk about things where we've got variables in our sums. So this is kind of a nice preview of all that. I'm going to continue this video, it's now getting a little bit long, in a second video where we look at telescoping series. We're also going to look at something known as the divergence test, and we'll do some sort of examples in the wilderness. Here are some series, do they converge, do they diverge, and so forth.